What's up, good people? Today we're talking about photons. It's pretty amazing. They're little crazy particles of the electromagnetic spectrum. We're talking photons. They're crazy. They're weird. So what is a photon? Well, I have it here. It's a particle of the electromagnetic spectrum. How about that? We could just end the video right there. Photons are pretty crazy. I've been learning more about them, and when I really dived into what a photon is, you really learn about physics at a very fundamental level. It's very fascinating what a photon is. It's also known as a quanta, or quanta kind of means like a tiny bit of something. That's where the word quantum comes from. So quanta just means it's like a tiny little bit of something. In this case, we're talking about particle. And quanta also means like a discrete packet or a discrete form of energy. So that's the way to think about photons, is like they're basically little tiny forms of energy, and they carry a lot of energy within them. Photons create light. They are part of the electromagnetic spectrum, which I have down here. They go from radio waves all the way to gamma rays. So this visible light that you see right here, this blue of my shirt that I have, that is visible light. So this is blue photons that you guys can see. So the white of the board here, the blue of my shirt, these are visible photons that we can see. But photons also exist throughout this spectrum. So there are radio wave photons, there are visible photons, there are gamma ray photons, and there's also X-rays as well. So a lot of these photons, all photons are throughout this electromagnetic spectrum, these waves and this light. Pretty crazy. Now, as I said, photons are not normal matter. Well, how can that be? Well, they have no mass. Photons are actually massless. They do not go to mass. How about that? These guys ain't going to mass. Photons are actually massless, which is just a crazy fact to think about. It's like, how can they not have mass? I don't know. They don't. They also are chargeless. So a lot of particles, like we know, are electrons. Electrons have negative charge. Protons have a positive charge. Neutrons are neutral. They don't have charge, so it's very much more like the neutron. It has no charge. So it's chargeless, it's massless, and they're not, because they're massless, they're not considered matter. They don't really matter. Sorry, photons. I mean, we could not see unless they existed, but we're honestly saying, oh yeah, they don't really matter. They're not normal matter. Pretty crazy. Just because they don't have mass. So if you look online or you do some research on this, you'll see it has zero rest mass. There's something called rest mass, which was confusing for me a little bit. And I was like, what do you mean? Photon is light, so if photons produce light, what do you mean it has zero rest mass? What is that? Rest mass basically means that it is never at rest. A photon is always moving. A photon is pure energy. A photon is constantly in motion. It's basically just energy. If you can get a big enough photon with enough energy, you can do the whole Einstein equivalence principle, where you can make that energy and it can become massive. So all that energy that's trapped in a photon can become mass. You can convert it into that, but honestly, it has no rest mass. It's never at rest. That's basically what scientists talk about when they say zero rest mass. This photon is not at rest. It doesn't chill on the couch. It doesn't want to sit down on the couch. It doesn't want to sit on a chair. It's like, I'm just going to chill here. So a photon is always moving, always in motion, always has velocity and acceleration. Pretty crazy. Just amazing to think about. And really, this comes online with our boy, Max Walk the Planck, as I like to call him. Mr. Max Walk the Planck. This dude, who we know him from the Planck length and H-bar and all this crazy quantum mechanics stuff. And scientists had noticed for a long time, one of the interesting things was they would see a lot of the energy get pumped into a system, but that energy would not then be released in the same amount. There was not an equilibrium going on. And this was happening with like radiation and other forms of energy. And scientists were very confused when they were studying particle physics around this time, the turn of the century, the turn of the 19th century. Max Planck, our boy here, Walk the Planck, he was kind of confused. Like, this doesn't make sense. Because if energy is pumped into a system, that system then should release that energy in the same amount. That was not happening. So he proposed that in fact, photons, this little tiny part, he didn't come up with the name, but he basically said these little tiny particles that are there, that exist, that they're trapped within a system. This energy is trapped, and it's only released in certain amounts. Quantization. Quantum. Welcome to the quantum revolution. But it's sort of like energy is contained until a certain amount is you can think of it like filling up a barrel. Like when you fill up a barrel or fill up a cup, once it reaches a certain amount, it overfills, then it spills out. Then the energy comes out. So only when that limit is reached, then the energy kind of spills forth, it comes out. And the same thing is true of photons. So he actually kind of was the first one to recognize that. And then we bounce over to our boy Albert Einstein, Mr. General Relativity over here, mega genius guy, 1905. He comes up with a further idea building upon Max Planck's idea and really gives birth to the quantum revolution. It was one of his miracle papers in 1905 that, explaining the photoelectric effect. What is the photoelectric effect of photons here? He basically added to Max Planck's idea. He said that, oh, light is not a wave. It's not a wave, guys, sorry. That was his initial concept. For a long time we thought it was just this waves, it was pure waves. But in fact he was saying no, it's actually little packets of energy. It's little tiny particles, these little tiny points. And when all that energy kind of pushes in, it shoots out electrons. And what happens is, we now know that, you know, electrons can absorb a photon or be shot out of atoms and stuff like that. And that's what's called the photoelectric effect, because it's photons pumping out or shooting out electrons. So sometimes they can interact and electron can be shot out of an atom. Einstein and Max Planck really helped start, and Niels Bohr and others, they really saw that photons were in fact waves and particles at the same time, also known as wave-particle duality. How about that? So we now know that photons are both waves and particles at the same time. When we're not measuring it, when we're uncertain about it, it's acting more like a wave. It's propagating throughout. When we do measure something and we do find it, it acts more like a particle. You can measure it and it has a precise amount of energy and discreteness and a quality to it that we can look at and define better with a particle. When we're not, it's a wave. Now this also interacts with quantum field theory, which is also fascinating. Quantum field theory really says that all particles, photons included here, are wonderful like particles. Photons themselves are part of this giant field. So in fact, when we measure a photon, it actually pops up as a particle. So really when we measure a particle, we're actually measuring a little tiny point on this giant field, or this giant wave, if you will. So you can imagine all these particles are just waves in an ocean, like I have my full wavelength here. So we can imagine that all these particles are just giant waves in the sea, in a giant ocean. And when you measure one of them, you're only measuring a tiny little point here on the wave. So in this giant ocean, you're actually only measuring a tiny little itsy bitsy point. That is a particle, at least as we understand it. So we're talking about discrete little points, discrete little packets of energy. Photons could just be like all other particles, where they're just tiny little blips on the cosmic ocean. So they're just on this giant field and little tiny points of visible light that we can see. So the sun is burned away 93 million miles away, but all those photons that come from the inner core of the sun, they burn and then they shoot out and they spread all their light to us here on Earth. Now all those photons, it takes them 8 minutes and 20 seconds to reach Earth. So photons are always moving at the speed of light. Remember, they never rest. Photons never rest for nothing. They're not on the couch. They don't like to chill. So remember, only in a vacuum does photons travel at light speed. It has to be a complete vacuum, like the vacuum of space. It has to be empty. So only in an empty space does it move purely at light speed. When it starts interacting with other materials like glass and underwater, the speed of light changes very, very slightly because the photons are interacting with other objects, other atoms, and they kind of gets in the way. It messes up their kind of flow. So this natural state is to just constantly move. So always think of a photon as always trying to go at light speed no matter what. If something interacts with it, it'll slow it down slightly because it's only interacting. But otherwise it's always trying to, light speed is this natural state. So in 1926, another super scientist named Gilbert Lewis, famous for the Lewis dot structures for electrons, or he was coming up with his Lewis dot structures for bonds and everything with atoms and chemistry. He was a chemist, scientist over here, Gilbert Lewis, but he came up with the name of photon. So he actually created the name. How about that? He's like, oh, this is a light thing, so we're calling it a photon. So I just wanted to throw his name out there too. I thought it was pretty cool. And that's all that we got to learn today about the amazing particles of light and the electromagnetic spectrum. They were discovered not too long ago, really formulated in the early 1900s, given a name in 1926 by Mr. Lewis. They are not baryonic matter, not normal matter, because they have no mass, they have no charge, but they are amazing nonetheless. They give us all the light that we see all the light that comes from the sun is pouring through with photons. And yeah, it's a bunch of energy, and maybe one day someone can harness more of the photons to give us an even better, bigger green revolution. That's all today about our magical, wonderful photons. Wherever you go, spread the light as much as you can. See you next time.